My name's Michael Howard. Actually, it's kind of cool being back in Barcelona. The last time I was in Barcelona was I was a kid. I don't remember anything except my mom and dad buying me everything. Now I've got to buy everything myself. But yeah, it's actually good to be back in Barcelona again. Although I did fly in just this morning, so I'm a little bit jet lagged. But anyway, before I get started on this presentation about the security development lifecycle, I kind of changed it at the last minute. Like every Microsoft presentation, it always gets changed at the very last minute. And I thought what I would do, as soon as this is a tech ed developer forum, I would just focus solely on developer things, as opposed to the rest of the SDL, which focuses on design and threat modeling and testing and post-release process improvements that you must do as well. I thought I would just focus exclusively on the developer-related things. So before I get started on this, who am I? Who the heck am I? I've been at Microsoft for 15 years. I've always been involved in security, which is kind of weird. Because up until about 8 years ago, my focus was almost exclusively security as in features, security features. You know, authorization, access control, authentication, ACLs, SIDs, tokens, privileges, all that sort of stuff in Windows. And then a small group of us decided to splinter away from the Windows group. And we were focusing, this is in 1999, end of 99. And we decided to focus on security as in threats to software. Like how can people compromise systems? Which is a very, very different way of looking at the world. Most people just look at the world as, you know, I know about security because I know how to deploy some security feature or use some security feature. Well, that doesn't really help that much, because if the quality of the code that is the defensive feature is, the quality of that code is poor, then you'll continue to have security vulnerabilities and security breaches. And so we splintered away to focus on security as in threats to software and the whole engineering process that goes into building more secure software. Our group now is well above 100 people. And you can think of our group as sort of a central security consulting group within Microsoft. And all we focus on is software security. That's it. Absolutely nothing else. And privacy. But basically that's it. We don't look at features. We're not going to build the next whiz-bang security feature. We focus exclusively on the quality of that feature from a security perspective. I'm also very much a pragmatist. I'll tell you one thing that's so true right now about security people, and I was this person as well for a long time. Basically, security people pretty much suck because they are really, really, really good at being very myopic and saying you can either ship this thing securely or it's not secure. It's black or it's white. It's secure or it ain't. Unfortunately, on planet Earth, it's not quite as simple as that, because you can't have something that's completely secure. Because if anyone tells you it's completely secure, they're lying. Then the other option is to have something that's completely insecure. Well, funnily enough, there are varying shades of gray in between. There really are. And the problem with a lot of security people is that they are very good at ignoring those shades of gray. They're very good at just saying it's secure or it's not. The other thing security people are really bad at is telling you how to do something right. They're very happy to tell you when you screw up. Very, very happy to tell you that. That's really stupid. Why are you doing it that way? Then you'll say, well, how do I fix it? I don't know. But when you do it wrong again, I will tell you it's wrong. And you know, that just builds up this really antagonistic relationship. And a lot of security people are just antagonists. They just love annoying people. I swear. And so one thing that I've learned, and if there's one thing that I think all security people should learn, is that there are varying shades of gray. Now let me give you a real good example. I spent nearly two years of my life working on Windows XP Service Pack 2. And we added this new defense to Windows XP Service Pack 2 called NX, no execute, also called data execution prevention. Long story short, it helps mitigate, helps prevent data from running, executing data. Because most vulnerabilities enter a system as data. and then you try to execute that. It's like, why are you executing data? You shouldn't be doing that. But the thing is, the CPUs never supported this capability. And so with Windows XP Service Pack 2, and with as it was then, the first wave of AMD devices, together we could actually support this NX capability. At the time, we really had two options. Option number one was disable it by default. That's just ridiculous. Because a security feature that is off by default, you may as well not even bother. You may as well not even bother building the feature, because if it's not on by default, people are not going to use it. Period. Just the way it is. And then here's another dirty little secret: when something is not on by default, it doesn't get tested as much. I can tell you that categorically. Actually, I shouldn't really be telling you that. The next option was to crank it all the way up to the top. In other words, it was on by default, and it was on by default for every single application that runs on the box. There is an ever so small downside to that. A lot of stuff doesn't work. For example, the Java VM didn't work. Why? Well, it's taking Java bytecode, data, interpreting it, writing out a series of bytes, and then executing it. Perfectly valid, but it violates NX. Flash failed to work. Adobe Acrobat Reader failed to work. A bunch of things all failed to work. So clearly, we couldn't crank it all the way up to 10, enable it by default for everything, because a lot of stuff just wouldn't work. So we're in this real dilemma. Don't install it by default, or don't enable it by default, or enable it by default and nothing works. What do you do? Well, I'm a security guy. I'm like, ignore the application compatibility problem. I'm a security guy. It's got to be cranked all the way up to the top. That way it's damn secure. Nothing works, but it's secure. Well, Rebecca Norlander, who was running the project at the time, got me in a corner and had a little chat with me. Basically said, shut up. You can't crank it all the way up to the top. We can't do that. Because a lot of stuff doesn't work. A lot of stuff doesn't work. People will not deploy this service pack. Now, and here's the problem. NX is just one defense of a bunch of defenses that were added to Windows XP Service Pack 2. So if we cranked it all the way up to the maximum strength, people would not have deployed it, and they wouldn't have been able to take advantage of all the other defenses we added to the service pack that were not NX. And Rebecca was absolutely right. And so what we did is there was a shade of gray, which was sort of crank it all the way up to 7, which basically meant that everything in the core OS was protected by NX. But if you had an app that ran on top of the operating system, you could opt in to have the operating system protect that application as well. But you had to opt in. You had to select that I want to allow my application to be protected by this. And I'll show you how to do that later. So one thing that I've learned, actually I've learned a lot of things in the last few years, but one of the critical things that I've learned as a security person is that there are these shades of gray, and you have to know where they are. And it's very, very hard sometimes. But you know what? No one said life was easy. So next time you see, talking to a security person and they're saying, don't do it this way, ask them, well, what's the right way of doing it? You'd be surprised how many times they don't know the answer. It's very easy, very, very easy to say that's bad without providing an appropriate solution. Along the way, I've written a couple of books. Probably the most well-known I did with David LeBlanc, which is Writing Secure Code. The one that I'm sort of talking about today mostly is this one. And Writing Secure Code for Windows Vista came out earlier this year as well. And I have a session sometime this week which goes through all the defenses that we added in Windows Vista and how you can take advantage of them from a programmatic perspective. All right, let's move on to the guts of this presentation. So what is the SDL? What is the Security Development Lifecycle? Oh, by the way, at the end of the week, I have another session called the Everything Security Developer something or other. And one thing I want to do at that, I have no slides. No slides. All I will do is open Notepad, and I'll write down some interesting ideas, and then we'll just talk for an hour and a half. And one thing I'd really like to go through at some point is the history of SDLs, how we got to where we got to. It's really kind of fascinating how we got to where we arrived at. So the SDL is pretty simple. It's a whole bunch of requirements and recommendations to help with the design, development, testing, and the post-release process. It's all about taking an existing product lifecycle and augmenting it with security and privacy enhancing techniques, as it were. The goal is simple. It's to reduce the number of vulnerabilities in the product, whatever the product is, and it's to reduce the severity of what you miss, because you're never going to get every single security bug, ever. And there's a very good reason for that, and that is because security is man versus man. This is not like reliability, which is man versus computer. That's an easy thing to fix, because the computer is not trying to attack you and trying to play silly games. Well, sometimes you think they okay, it's not intended to play silly games. Whereas in the case of security, oh, the other guy wants to take you down, and he will spend as long as possible to take you down. And he will take as long as possible to compromise your banking software or your website, if it's worth it to him. So this is an ongoing arms race. So two of the mantras in SDL are secure by design, secure by default. Secure by design is all about trying to get the code and the design right. And secure by default is recognizing you never will, which is all about trying to reduce the attack surface and containing the damage, because you will be compromised, you will be attacked. And the last point here is SDL works, and we have empirical evidence to show this now. I want to throw something out there which is very, very counter to what a lot of people think. A lot of people think that you can just raise the quality of your software by adopting some quality thingamajig, and security will improve as well. We have no evidence to show that. We know of absolutely no evidence that shows that if you improve the quality of software, you will also improve the security posture of software. We see no evidence. Whenever I hear people say, well, just improve the quality and you'll get security for free, I always ask them, where's the evidence? Because I see none. And I've been asking that question now for 5 years, and no one has ever given me empirical evidence to show it. If you want to improve the security and the privacy capabilities of your software, you must focus on security and privacy. You can't just think about general quality stuff. You've got to really focus on them. It's a really weird field, but you've got to focus on them. So one of the metrics that I personally use for whether SDL works is the number of vulnerabilities that we find post-ship. The reason why I like to track that is because the security bulletin, to me, and I think to many customers that I've spoken to, the security bulletin is the unit of pain. And you want to drive that down. It's much better to deploy 5 patches than to have to deploy 100 patches. It still sucks. 5 patches still sucks. But it sucks less than 100 patches. And I'm a big believer in sucking less. I don't believe we'll ever achieve perfection, but we will certainly suck less over time. I believe that wholeheartedly. And so one of the metrics that I use is bulletins and vulnerabilities. And for since Windows Vista has been released, we have fixed 70 vulnerabilities in Windows XP and 33 in Windows Vista, about a 50% reduction in vulnerabilities. Now I'll take that. I mean, in a perfect world, that would be 0, but we don't live in a perfect world. So I'm very happy with that, very happy. It's actually on track with what I think we will end up seeing, which is about a 50% reduction in vulnerabilities. Now, something else that's not in this slide, and I really should update the slide, is the severity of the vulnerabilities. Critical, important, moderate, and low. because a lot of the bugs that are coming out that are being fixed may be critical on Windows 2000, important on Windows XP Service Pack 2, and low on Windows Vista. We see this a lot, a heck of a lot. We're seeing a similar trend in Office. We're seeing a similar trend in SQL Server. The last time we issued a security bulletin in SQL Server was 4 years ago. We're seeing a similar trend in IIS 6. Since the release of IIS 6, which was nearly 4 years ago, we've issued 3 security bulletins. And what's fascinating is those 3 bulletins are all shared in common with IIS 5. Now remember I said that the goal of SDL is twofold. Reduce the number of vulnerabilities, reduce the severity of what you miss. In the same time period, we fixed 5 vulnerabilities in IIS 5 versus 3 in IIS 6. So we reduced the vulnerability count. What's fascinating is those 3 bugs in IIS 6 are all lower severity than in IIS 5. Why? In IIS 5, those features are all running by default. In IIS 6, they're not running by default, not one of them. So unless you opted in for that functionality, you don't even need to apply the patch. In fact, in one of them, in IIS 5, you can't even turn off the functionality. It's WebDAV. In IIS 6, it's modular. You do WebDAV or you don't do WebDAV. It's up to you. And by default, you don't do WebDAV. So we're seeing this in all the products that are being touched by SDL. So it's goodness. It's goodness. We have empirical evidence that it does work. And the last little bit of sort of marketing I'll give you, and then I'll get stuck into the technology, is even the analysts have started recognizing that this is working, which is great. So again, if you want to increase the security position of your software, you've got to focus on the security. You can't just focus on the quality. You've got to focus on security. And that's the whole point of SDL. It's nothing else. All right, this is the SDL. Basically, the green bit is the SDL. What we did is take our existing lifecycle at Microsoft and added security and privacy enhancing requirements and recommendations along the way that you must complete before you can ship. I'm going to focus on one area. And I'll be frank, it's not even the whole area. I'm going to focus on just some of the key points that you can use today that are fairly easy to use, actually really easy to use, and will lead to a huge reduction in vulnerabilities just by themselves. There's a lot of this up front will be C and C++, and towards the back it will become more managed code and web related. The SDL is made up of 2 big chunks, requirements and recommendations. Requirements are stuff you must do. Otherwise, you're not shipping. And recommendations are just good ideas, things that you probably should do. But would never stop you from shipping if you didn't use those recommendations. So the first one, and this is an ongoing area of research, is there's some functionality that's available to us today that was invented a long time ago, and it was fine 20 years ago. The problem is the threats have changed. We now have the big bad internet. We never had that really 20, 25 years ago when this functionality was invented. The most well-known are the C runtime library functions. They were fine 20 years ago when the threats were different. Well, the threats are very severe now, and we need to get rid of those functions. Over time, we just need to get rid of them. And one of the things that we say at Microsoft is that you can't write new code that uses any of these banned functions. You just can't use it. You've got to use safer functions instead. In Windows Vista, we went one step further. We actually removed the banned APIs from the code base. Just shy of 500,000 function calls. It took 5 years to do it. But it's worth it. Those problems just kind of go away. So we banned about 120 functions, and here they are. Good news is you don't need to remember this slide because Visual C++ 2005 will automatically deprecates a lot of those functions. So if you get a 4996 warning, you've got a function that needs to be replaced, which is very, very cool. If you're using a different compiler or you're not using Visual C++ 2005, you can include a file called ban.h, which is available in the SDL book. And it will work with GCC and with Visual C++, and it will just deprecate the APIs. Then there's replacements. Remember I said that security people are really, really good at telling you something's broken, but really, really lousy at telling you how to fix it? Well, one thing that we have in the SDL is that if you put forward a requirement, you must be very, very prescriptive about what the fix is. You can't just say, that's bad. You got to say, that's bad, here's how you fix it, and here's how you verify you fixed it right. You got to do all that. So we recommend strongly two libraries to use over the old C runtime libraries, the Safe CRT and StirSafe. They are different. The Safe CRT is on a fast track right now to go through ISO standardization, which is actually very, very cool, because it would just become part of the C runtime library. The StirSafe library was actually invented in the Windows shell team to solve a very specific problem. We made it publicly available. So you can use either. I use Safe CRT. And it's available in Visual Studio 2005. The other cool thing that we added to Visual C++ 2005 is that at compile time, if the compiler knows the buffer size, it will automatically migrate from this potentially unsafe function call to the safe function call. And we found about 50% of the function calls will get migrated automatically. So the source code doesn't change. It's just the generated object code that gets changed by the compiler. And you don't get the 4996 warning. So it's just sort of done quietly. But about 50% will just go away. You'd be surprised how many times the compiler knows the destination buffer size at compile time. One of my favorite tools that we added to Visual C++ 2005 is a thing called SAL, the standard annotation language. I will go through this in much more detail in my Vista talk. But basically what it is, it's a way of helping static analysis tools find more bugs. So I'll tell you a little story. There was a point, it was quite a while ago now, where the shell team in Windows were kind of flatlined on bugs. There were really no new bugs coming in. It was just noise, just flatlined on noise. And one of the engineers decided to use this new technology that had come out of Microsoft Research called SAL. Our tools knew about SAL, our static analysis tools knew about SAL. And what he thought he would do is actually go in and annotate the shell headers, the private headers used in the shell. And he did. It took him a few days. And then he reran the tools and found 100 bugs. Because the annotations add so much more contextual data about the way the function should be called. So let me explain what I mean by this. So let's say you've got this function called fillString. And it takes 3 arguments. One's a buffer, one's the size of the buffer, and then what to fill the buffer with. There's 3 arguments. Well, the first 2 arguments are linked at the hip. Right? They are completely related to one another. This thing is this big. Actually, more accurately, this thing is this many characters long. So you know that because you either A, wrote the function, or B, it says so in MSDN. Well, the compiler has no clue. It has no clue that those 2 arguments are related. Yet they are explicitly linked at the hip. The compiler has no clue. With SAL, you can link them together. Now, the SAL annotations are just macros. That's all they are. You just pound include sal.h, off you go. That's basically it. At that point onwards, when you start adding these annotations like the stuff in red, the tools will find tons more bugs. So what this means here, I'll explain it. So there's about, I don't know, 150 or so discrete annotations. And you tend to gravitate on about a dozen. And this is a really common one. So what you're doing is you're saying, actually I just want to go back. You're actually saying this thing here is an out buffer. You're going to write to this buffer. You're not going to read from it. Right? You're filling the string, not read and fill string. You're writing to the buffer. That's it. It's an outbound buffer. and its element count is CCH buff. In other words, this thing is this many elements big, and that's it. So all of a sudden, the compiler knows, or the tools know, the relationship between these two arguments, whereas before it didn't know, had no clue. So there's other examples of this. This could be in, which means we're going to read from it. Could be in, out. We're going to read and write. This here could be a B count, which is a byte count. There's a whole bunch of others as well. You can also annotate function returns. So malloc, if you go and look in Visual Studio today, and just go and look at the, open up, was it malloc.h or memory.h? I don't know, malloc.h, and look at the function prototype for malloc, you'll see that it's this. Check return. You've got to check the return value from malloc. Otherwise, you're just going to leak memory. Now, if you don't check anything, you're just going to leak memory because you don't get a handle back or a pointer back to free. So you've got to check the return value. And the other thing is that the return value is a byte count optional of size. Malloc will allocate this or nothing at all. It won't allocate size plus or minus a random number. Well, that would be fun. It allocates size, or it fails. So what this means here, this opt, means optional, which means that this can return null. If this is not optional, this can never return null. So if you look up here, this is an outbound buffer, its element count is this big, and it's not optional. You cannot pass null into fill string. You can't do it. Well, you can, but if you do, the tools will detect that you've got a bug in the code. Because it makes no sense to write to a null buffer. So you take this code, so this code fragment, if you actually don't include the annotation and you run this through Visual C++ 2005 at warning level 4, you get no warnings. None whatsoever. You do /analyze, no warnings. Then add the annotation, you get a bunch of bugs. Actually, you get 2 bugs. One is basically saying, hey, you're allocating 200 elements and trying to copy 210 elements. Well, duh. I mean, okay. That's pretty straightforward. But the other one's interesting. Argument 1 might be 0. The return value from this might be 0. It might be null. But this thing up here does not allow null. There's an impedance mismatch. You got a bug because you're not checking that malloc actually succeeded correctly. So just using Sal of all the technologies that we have, I think Sal is one of the most exciting, and it's available for free in Visual Studio today, in Visual Studio 2005. All right, moving right along. So integer arithmetic. Everyone calls these things integer overflow problems. They're not. They're integer arithmetic problems. And there are 3 classes of integer arithmetic problems: overflow, underflow, and signed. Overflow and underflow are sort of lumped together: truncation and signed versus unsigned mismatches. Very, very common bug today. C# also has them. The big difference is that in C and C++, you end up with a buffer overrun. In C#, you don't. But you may get an exception thrown, which means your application may crash. VB will automatically detect the overflow and actually throw an exception as well, which you can catch. So one of the ways of mitigating integer overflow problems, one of the first things to do is to actually use the latest version of the compiler. Because one of the overflow conditions that people never really thought about was calling operator new. So calling operator new, there's actually a multiplier that goes on. The number of objects multiplied by the size of an object. Allocate that amount of memory, and then call the constructor as you walk through the memory. The problem is, if that overflow, if the bad guy controls the number of objects, he can provide a number that overflows past 2 to the n, 2 to the 32nd, or 2 to the 64th. If you don't allocate enough memory in the overflow. The coolest thing here is that we, must have been 4 years ago now. No, perhaps not 4 years. No, it'll be 4 years ago. we were thinking about this. We thought, I wonder if we could put a defense in the compiled code. And one of the guys that I know in the back-end optimization team said, yeah, I can do the check in like 6 or 7 instructions. And so what he did was so when you actually call operator new, the compiler will automatically, right before the call to operator new, verify there's been no overflow condition in the multiply that goes on. And if there has been multiply, then the call to new will essentially fail. Now, that may lead to your application crashing, which sucks. But it sucks less than running exploit code. Remember, I'm a big believer in sucking less. So a good example of that actually is earlier this year, there was a bug in VML processing. That vulnerability was a low severity vulnerability, yet it was critical on every other platform. On Vista, it was low severity. The coding bug was there, but it was still low severity on Windows Vista. Critical on every other platform. You could get exploit code to run. Why? Because of this. We compiled it with a new compiler. We detected, it was actually an integer overflow calling operator new. The bad guy controlled the number of objects. We just detected the overflow and just killed the process. Again, it's not great, but it's a heck of a lot better than running malicious code. The other thing you should always do if you're writing in C and C++, and this is so important, I can't even begin to stress how important this is go and identify every piece of code that allocates memory dynamically. Whether it's like alloc, alloc A, malloc, global alloc, local alloc, realloc, whatever. And ask yourself this question. First of all, is there any kind of calculation that goes on to calculate the buffer size? If the answer is no, move right along. The next one is, if the answer is yes, there's some kind of calculation that goes on, does the bad guy control one or more of the operands? If the answer is yes, you have a 100% bona fide security bug that has to be fixed. So I want to state this again because it's really important. Go and identify every single dynamic memory allocation you have in your code, C and C++. Determine if it's a constant. If it's a constant, there's no calculation going on, the bad guy doesn't control anything. If it's just a constant, move on. It's not a bug. If the bad guy controls something, then you've got a 100% bona fide security bug. We also have a couple of defenses. We have IntSafe and SafeInt. We could have come up with better names, I know, but IntSafe was born in the Windows division, and SafeInt was written by my co-author, David LeBlanc. If you're writing in C, just use the IntSafe stuff. If you're writing in C++, then use LeBlanc stuff. Which the C++ stuff has a whole bunch of very well-written templates for doing very safe arithmetic. So here's a pop quiz. Does anyone care to tell me whether this is a security bug or not? So let's just walk through it. I take some value. I add that value to some constant. It doesn't even matter what the constant is. I then allocate that number of things. If this thing does not return null, then copy some data and then return the pointer. And assume, obviously, the caller must free the pointer. So is it a security bug? Well, so here's the issue. The first look at it, the answer is potentially yes. The real answer is, does the bad guy control that CB alloc? If the bad guy controls it, you've got a 100% slam dunk, bona fide, card-carrying security bug. If the bad guy doesn't control CB alloc at all, let's say, for example, only admins can control that value, or perhaps it's a constant that's just passed in as a value, as an argument, then no security bug. With that said, if I saw this code, I cannot predict how this code will be called in the future. I have no clue. So I would definitely change this code. In this case, I'm using IntSafe. It'll do the appropriate addition, and if it fails, then you overflow or underflow, and it will not actually perform the memory allocation, which is the right thing to do, return null. So it's pretty easy to change this code to make it safe. All right, that's all I want to talk about buffer overflows. The rest of it's kind of primarily relates to almost any language. But I wanted to get some of the really horrible, deep, horrible bugs out the way. Next one is no weak crypto. The funny thing about cryptography is that it's, in the last few years, it's really come under a lot of scrutiny. A lot of scrutiny. And a lot of things, a lot of algorithms that may have been okay a few years ago are just not okay today. They're not. So at Microsoft, and I'll caveat at Microsoft, I'll show what I mean by that in a moment. No new code can use MD4, MD5, or SHA-1. MD4 and MD5 hash functions, they're now officially broken. On a normal PC, you can get a hash collision at a rate of 1 a minute with MD5. That's really bad. You should not be able to get hash collisions like that at all. So MD4, MD5 are officially busted. SHA-1 is already showing signs of serious weakness. So we've basically taken a very bold move and just banned it for new code as well. Because we reckon that if you're building code now, that code will probably have to be supported for 10 years. You know, say in the case of Windows. Will SHA-1 be busted in 10 years? Yeah, I think it will be. I actually really do. Now you must use the SHA-2 suites. So that's at Microsoft anyway. You know, SHA-256, SHA-384, or SHA-512. Can't use DES. Anyone care to guess why you can't use DES? Key size is too small. A 56-bit key is ridiculous now. It was fine 10 years ago, but it's not fine today. So you must use AES. We don't even allow triple DES. We don't even allow it. Now, I remember I said before, at Microsoft, and then I'll caveat this, there are many cases where we do let new code go through with these weakened algorithms, and the reason is for compatibility. Here's a good example. Digest authentication, you got to use MD5. And digest authentication is an RFC. It's a standard RFC. Everyone implements digest and they use MD5. We can't just rip MD5 out and replace it with SHA-256, because guess what? We won't be able to interoperate with anybody. It'll just not work. So it'll be damn secure, but you can't use it. What sort of use is that? Back to being pragmatic again. Sorry? Oh, your WPA, yeah, MD4. Yeah, just gets worse. So the question was about triple DES. Yeah, it will allow triple DES through if the standard to which you're building something requires triple DES. So for example, SSL, one of the options is triple DES. We can't just yank it out. It's part of the standard. But if you're building something that doesn't have to interoperate with, with something like that, or has no backward compatibility implications, then yeah, you can't use triple DES either. Now here's one for the crypto guys out there. Why have we banned RC4? The question is there any real standards around, you mean like around which algorithms thou shalt use? Oh, I see what you mean. So RC4 is technically a trade secret, and its algorithm was never technically documented, but everyone knows what it is. So, but that's, I mean, we implement RC4, because we bought the RSA, the code from RSA, so it's just a black box to us. But the reason for not using RC4 has got nothing to do with standards whatsoever. So if you're going to, implement something that used a billion-bit RC4, we would still say no. Why? It's not what? That's not the reason at all. Why? Actually, it has been scrutinized a great deal, because everyone kind of knows how it works, to be honest with you. And it has been scrutinized. That's not the reason. The reason is it's a stream cipher. And if you want to build something with a stream cipher, you've really got to know what you're doing. Really got to know what you're doing. Because they're open to very, very easy attacks. So the way RC4 works, basically, now bear with me, it's essentially a big random number generator. That's it. And no one actually knows where the cycle starts again. No one knows. And the key that goes in is just the seed. That's it. That, in a nutshell, is RC4. So what happens is the first byte of ciphertext, the key stream comes out, and you XOR that with the first byte of the plaintext. And it gives you the first byte of ciphertext. Next byte, the next key stream byte, next byte of plaintext, XOR together, next byte of ciphertext, and so on and so forth. Here's the problem. If you reuse a key, you're in deep trouble. If you take two documents and you encrypt them with the same key, even if it's a gajillion bit RC4, all you need to do is take one document, XOR the content with the other document. You've now got the XOR of the two plaintexts. It's a lot easier to crack. But it gets worse. If you know one of the plaintexts, all you need to do is XOR your plaintext with your ciphertext, get the key stream back. XOR that with the other ciphertext, and you've now got the plaintext back. But it gets worse. Because it's a key stream cipher, a stream cipher, which is encrypting one byte at a time, you are subject to bit flipping attacks. You don't really know whether a single byte has been changed. Let's say I know the message format is attack at some time using a 24-hour clock, Zulu. So it could say attack at 1200 Zulu. I can't read the message, but I know the message format. And I know that I can intercept the message as it goes between the two parties. Intercept the message. I know that the last 5 digits, last 5 bytes are time, Zulu. I know that. What I could do is flip one of the bytes. I'm not decrypting it. Just flip one of the bytes and then shoot it across to the other party. When they decrypt it, it may decrypt to attack at 1300 Zulu, at which point the enemy's already waiting for you. You never decrypted the message. You did a bit flipping attack. With block ciphers, it's harder because if you change one byte in a block, you corrupt the entire block. So it becomes easier to detect. So stream ciphers are really, really, really hard to get right, to use correctly. And so we will always try to talk you off the ledge if you're trying to use a stream cipher. Moving right along, no weak random number generation, no embedded secrets. The last one is interesting, is be crypto-agile. What that really means is do not embed your cipher information or your crypto algorithm information into the code. You're calling managed code, and you hard code the triple DES provider. Well, what happens if all of a sudden tomorrow triple DES is found to be fundamentally broken? Now what do? Do you go and change all your code and then deploy it out to all your customers? Probably. What happens if the block size is different? Now your message size is all different. Your key size is different. Your initialization vectors are different. Your salts are different. So what we do instead is you can have like these sort of crypto factories, and you can have it more sort of configuration driven, as opposed to being hard-coded. So don't go hard-coding algorithm names into your application, because if the algorithm is busted, you're busted too. You're going to be able to configure that on the fly. No weak ACLs, this applies to absolutely everything. No weak access control lists on objects, period. You've got to be very careful here. One weak ACL can render the entire operating system vulnerable to attack. I'll give you a good example. There's a bug that we found, it was a couple of years ago now, where a vendor, I'm not going to name the vendor, they actually installed their own device driver on the box. It's a third-party setup. And they copied their device drivers into the program files directory. Just like program files, whack, company name, whack drivers. No problem. The problem was they changed the ACLs, the access control list, to everyone full control, which basically means anyone can write or do anything in that directory. Anyone. Here's the attack. I write my own device driver that's got exactly the same name as their device driver. I overwrite their device driver with my device driver. When the OS boots, I'm now running in kernel mode. Simple as that. Dead simple. I'll show you another variant of that. Let's say you have a very, very strong ACL on the program files directory, but the registry, the key in the registry that points to the location of the driver, let's say the registry key is ACLed insecurely. You know, everyone full control, for argument's sake. All I need to do is take the same driver that I just wrote, update the registry to point to somewhere where I can write, like my profile directory, plop the driver in there. When the system boots, it loads my driver into memory, because I've changed the OS to point to the location of my driver, because the ACL on the registry key allows me to. So you've got to be very, very careful about the access control lists. Here's Michael's rule of thumb. Basically, don't get yourselves in the ACL game. If you've got any code in your setup that changes ACLs, my first recommendation is to comment that code out. Especially if you're deploying on Vista or later. Well, actually, Windows XP SP2 or later. Because the default ACLs in the OS are very, very good. So if you're going to drop to the program files directory, you're fine. You're going to drop to the System32 directory, you're fine. If you start manipulating those ACLs, you know, you may loosen the ACLs, and we spent a lot of time trying to get the appropriate ACLs in the OS. Some compiler requirements. We are exceedingly hardcore about this, extremely hardcore about this. So one thing that we've done over the last few years, and we will continue to do so, is update the defenses that we can add to the compiled code. And some examples are, I'm going to go through all these in a minute. There's a GS, which is a compiler switch, dynamic base, NXCompat, safe SEH, which are linker flags, and then strict, which is a middle flag. The good news is for a lot of these, certainly for GS now in Visual C++ 2005, if you don't do any GS stuff whatsoever, you get GS for free. It basically helps detect certain kinds of stack-based buffer overrun at runtime. We will continue to add these defenses, and when I do my Vista talk later, I will demo all these defenses and show you how they all work and how they stop attacks. So GS, we're now into our fourth generation of the GS defensive technology. Essentially what it does is it adds a random number to the stack to every function call, well, an affected function call stack, an affected function stack, I should say. It also changes some of the data around. So for example, if you want to override the return address for the function, you've got to guess this cookie value, because we check that when the function returns. And if that's changed, we kill the process. Something overran the stack. We also swap, in the old days, we would have buffers and then non-buffers. The problem with that is if this up here was like a function pointer, you could easily overrun the function pointer. Whereas here, you've got to get a buffer underflow, which is a lot harder to pull off. Not impossible, but a lot harder. The other thing we do for certain kinds of arguments is, so the reason why we added this was really kind of interesting. When the blaster worm came out, or when we were notified of the bug, the guys that found it were 4 guys in Poland who were a research group called The Last Stage of Delirium. These guys are wicked smart, brutally smart, and they all now work at Microsoft. They're really, really clever guys. I'd rather have them on our side than on the other side. Well, they found a way. So when Blaster came out, a lot of people don't know this. But when Blaster came out, Windows 2000 was infected, Windows XP was infected. And I'm choosing my words very, very carefully here. Windows Server 2003 was not infected. but the coding bug was there. It was affected, but not infected. What I mean by that is we actually detected the buffer overflow at runtime. We detected it, and we killed the process dead. The downside is the process that got killed was RPCSS, which has this ever so small side effect of blue screening the box. It still sucks, but it sucks less than running exploit code. That's why I said it was affected, not infected. The guys that actually notified us of the bug had found a way around the GS flag, but it was never made public for a long, long time. Otherwise, there may very well have been a variant of Blaster that could have infected Windows Server 2003 machines. Without going into all the horrible, icky, gory details, there were some really interesting arguments being passed into the affected function. They basically clobbered all this data such that they could actually patch the address that was used to call the code after it detected a GS failure. They patched their code to, they patched the address of the handler to point to their shellcode. So when the function started to shut down, say, oh my goodness, there's been a buffer overflow, call the GS code, it called their shellcode. Kind of bad. So one thing we added in Visual Studio 2005 is for certain arguments, we actually copy them into lower memory and then work on those, not on those, for certain kinds of arguments. That would have prevented the LSD attack as well. So the version of GS that we have now, so Windows Vista, is actually compiled with the Orcus compiler, the Visual Studio 2008 compiler. And that's got the latest and greatest GS. There's, right now, as of this minute, we know of no way around it. That might change tomorrow, but right now we know no way around it. Safe exception handling, this is just a linker flag for crying out loud. That's all it is. The GS, you just go whack GS. And safe SEH, just a linker flag. That's it. What this does, this would have prevented code red. Essentially, code red whacked an exception handler on the stack. It didn't whack a return address, just an exception handler. So when the exception was raised, it called into their exploit code. So when you link with safe SEH, we look at the address of the destination address of all exception handlers. We write those addresses into the PE header of the executable. When an exception is raised, the OS says, hang on a minute, where do you think you're going? Looks at the address you want to go to and looks it up in the PE header. If that address is not on the list in the PE header, we kill the process because something corrupted the exception handler on the stack. And again, that alone would have prevented code red. A couple of other important, very important flags, in fact, you should really use these together, are NX-compat and dynamic base. And again, in my Vista talk, I'll actually go through both of these in detail and give you coding examples. NX-compat means that I want to be protected by the NX, the no execute capability of the CPU. Just about every CPU today supports it. So it's free, essentially free. So if you know your application doesn't do funky stuff, doesn't try to get data, morph it, and then run it, link with NX-compat. At that point, you'll be protected by the CPU and the OS. Next one is dynamic base. This is one of my favorite features we added to Windows Vista is address space layout randomization. So essentially, when we boot the OS, we put it into one of 2 to the 8th configurations. The net effect of that is the bad guy can no longer easily predict the location of his code in memory. More importantly, he can't predict the location of particularly sensitive DLLs in memory, such as WinSock32. Because they're going to call that because they'll call load library, then they'll open wsock32.lib or .dll, I should say, and then get proc address for socket, then get proc address for WSA set socket option. And they'll start doing their own socket function calls. With this capability, it makes it a lot harder because it's harder to predict where WSock32 resides in memory. In Windows XP Service Pack 2, it's easy. It's there. You boot the box, it's there. You go to another box, it's there. In Windows Vista, that's not the case. You got basically you got a 1 in 256 chance of getting it right. Which means that you got a 1 in 256 chance of getting it right. But it's better than getting a 100% chance of getting it right. Sucks less. The net effect of that is that you'll probably see your app, if they're under attack, you may see them crash more often, rather than not crash at all, because they've been compromised, successfully compromised. The other cool thing that we do is we move your stack around. So if you actually create a thread, it will automatically offset the start of that thread by 0 to 31 pages. Then when we know what page it is, we'll offset inside that page. And then your thread start address will start at that address. It's a random address. We also randomize the heap, but that's got nothing to do with this, but we also randomize the heap in Windows Vista, and you get that for free. That's just there anyway. So dynamic base is really, really useful, very useful, because it just makes it a lot harder for the bad guys to predict where their stuff is in memory. Next one is, this has been around for a long, long time. All this does is it makes, if you're using RPC or DCOM, anyone still using RPC or DCOM? Moving right along. Okay. So there's one thing I want to talk about tools. I want to talk about tools before I get into the last section. I love tools. I think tools are incredibly useful. By tools, I mean static analysis tools, by stuff that you can do in the compiler or in the language. Those are kind of tools. Those kind of tools. I really love tools. The problem is if you're going to go into the software development process with little discipline, no tool is going to help you. If you don't understand what the fundamental security problems are, no tool will save your backside. No tool. And unfortunately, I've seen people make this mistake many, many times. They, take some of the monkeys off the works of Shakespeare for a while, write some junky code, pass it through a bunch of tools, and give it a big thumbs up at the end. I'll be honest with you. If the code is crap at the outset, it's not going to get much better, no matter how good the tool is. The real thing is, don't hire bad developers. That's what it boils down to. It does. That's what it boils down to. And unfortunately, what we're seeing right now is people are just cranking out like Web 2.0 apps like there's no tomorrow. And it's crap. A lot of it's really bad code. No tool is going to help you. There are some fundamental things that you should know as a developer. I'll tell you another story. This is a story that's stuck in my head forever, and probably will be in my head until I die. When we were really started on this long journey, one of the first things we did was educate absolutely everyone within Microsoft. If you had an engineering position, we assumed you knew nothing about security, which turned out to be correct. But at least that's a good assumption to start from, right? Can only get better at this point. So what we did is we put everyone through security. But here's what we did that was absolutely critical. For every single training session that we did, we had a vice president kick it off. Just for 5 minutes. Blah, 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 security, blah, 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 important, bye. I mean, it was really simple. One of the sessions that I had, we had the vice president of the base, which is basically the kernel down in Windows, an Irishman by the name of Rob Short. He is less politically correct than me, and he's a VP. But basically, he said this, which is so damn true. What is it about security that makes it special? Why do we always have to come to the high priesthood of security to find out what the right way is of doing something? That's ridiculous. There is nothing, these are his words, there is nothing special about security. It should be part of getting the job done. Period. Over to you, Michael. And that's basically how it went. And he was so right. There is nothing special about security anymore, yet we still treat it as something that only the gurus understand. That's ridiculous. Everyone needs to have a baseline of expertise in this industry. Because you know what? How many of you build software that at some point is hooked up to the internet? The rest of you are lying, all right? Everything gets hooked up to the internet at some point. It might not be today, it might be tomorrow. And that's the real problem, is when you build something thinking it's not going to be hooked up to the internet, and then tomorrow it is. Like Windows 98. I'm serious. It was never built with real hardcore internet connectivity built into it. It never was. So this is why all your developers, all your designers, your management, your testers, your release people, they need to understand the baseline of security. They need to. Because they're just going to keep producing junk otherwise. That will get whacked one day, get compromised one day. And that may really put customers at risk. Or more interestingly, put customer data at risk. And we're in Europe right now. The rules are a little bit harder. In the US, not so hard. In Europe, a lot more difficult. So it's really important that you use tools as much as possible, but remember, they will not save your backside. You've got to have good, disciplined engineers. There's no replacement for that. There is no replacement for human intellect. One last little defensive measure that I want to talk about is in Windows XP Service Pack 2, if we detect any kind of heap corruption, we just leak the memory. The problem with that is it becomes very, very hard. Well, your app just keeps running, which is great. But actually, it's not great, because the thing will blow up 3 weeks from now, and the insides of the application are just mush, because it's been corrupting memory for the last 3 weeks. We've just been leaking memory, and you see your working set slowly going up. So in Windows Vista, there's the option, and you can just call this little API. And if we detect any kind of heap corruption, kill you dead on the spot. The reliability guys, they don't like that, because reliability goes down. Security goes up, though. It does. Because all of a sudden you can't compromise it, because it's dead. We had a bug that we had to fix. I'm not going to name any names. We turned this on in IE for Windows Vista. And a third-party ActiveX control had a heap-based buffer overflow in it. And we were picking it up because of this. And we never picked it up prior to this. It wasn't our ActiveX control, it was a third party. And our stress tests picked up the bug just like that because of this. And the control got fixed, which is exactly the right thing to do. The other option could have been to back this change out. I don't think so. Not when you're talking about a web browser. So from a reliability perspective, yeah, it sucks because your apps crash quicker. But at least you got a nice clean stack trace right to exactly where the failure is. You fix the bug and get on with life, rather than feeling happy because your app's just running all the time, but internally it's just soup, because it's just corrupting memory all over the place. Feels good because it just keeps running, but in actual fact, it's totally unreliable. That's a really, that's a very good question. Do I see much conflict between reliability and security? And the answer is categorically no. The reliability guys love us, except for one scenario where they loathe us. But I don't care. That one scenario is if you've got a Windows box in common criteria mode and the security event log fills up, we blue screen the box. By design, it's not a bug, we blue screen the box. Why? Because if you cannot log any more security events, you can't use the box, period. And so we blue screen the box. That's the only time. Because in fact, here's another little mantra. In fact, if you get hold, I see actually in your packs, there is the security issue of MSDN magazine, and there's a column I wrote in there. I write for it every year in the security edition. There's one in there which is basically stuff that we learned in the last 5 years. And one of them is this. Today's DOS, denial of service, reliability, is tomorrow's exploit. Often an exploit is just a bit more work away from a DOS, denial of service. So 99 times out of 100, when we fix a security bug, it's very often a reliability bug being fixed at the same time. In fact, I've seen too many bugs get postponed as pure reliability bugs, and they're not. With a bit more work, you can turn them into real bona fide security bugs. Next one is, and the other one, that I'm surprised you didn't ask me this question. Do you guys ever get into big slanging matches and big fights with the performance guys? The answer is no. You know why? Everyone thinks, it drives me freaking nuts. Everyone thinks if you do all the security stuff, then performance will suck. I have one thing to say to you. Measure it. Don't just say it will suck. Measure it and give me the results. I'll give you a brilliant example. I gave two solutions up there for solving integer arithmetic problems, int safe and safe int. We actually have three solutions at Microsoft. The third one is still available, but no one uses it. Happens to be the one that I wrote. But here's the funny thing. Mine is written in handcrafted, ultra-high speed assembly language. David LeBlanc's safe int is 80K, a big, fat, slow, bloated C++ template code. Dave, great guy. He probably knows more about integer arithmetic problems than anyone on the planet. Anyone on the planet, seriously. The guy's a genius. So one day I'm saying to Dave, Dave, I love you, but you know what? Why would I use your big, fat, stinking, slow C++ pile of garbage when I've got my hand-tuned, runs like a Norwegian racing herring assembly language? And he says to me, let's test it. Let's benchmark it. I did. You want to know the horrible truth? His is faster by 5%. Why? So I immediately email some good buddies of mine in the back-end compiler. What the hell's going on? Why is my assembly language not running really fast, whereas Dave's is running really, really fast? The reply was beautiful. You're a moron. Oh, thank you. I needed some affirmations today. Thank you very much. Now, could you mind explaining things? So yeah, basically when we, the compiler, generate the code, we know all the assumptions we made about generating that code, which means that we can optimize it. You just gave us this stinking pile of assembly language. We just treat it as a black box. We don't know what it does. You just shut down a good chunk of the optimizer. So the real reason why his ran faster is because they could optimize it to death. My stuff couldn't optimize it. A lot of assumptions you can't make, especially when it comes to aliasing and things. And mine was using pointers all over the place, but it shuts down all the aliasing optimizations. So whenever you hear people say, well, you can't do it this way because, my reply is always the same: measure it. Don't just use some gut feel. Measure it. Then let's make a decision. At least that way we'll have the facts. All right, next one. Web-specific requirements. These are things that, again, are in the SDL. A lot of this has been driven primarily because of the Windows Live guys, MSN guys, but primarily the Windows Live guys. We're still seeing across the industry the same mistakes that were made years ago. They're still being made. They're just being made a lot faster now. People are producing a lot of Web 2.0 junk really quickly. It actually reminds me of the old internet war days. The old internet wars, you know, the browser wars, where people were producing like code really, really, really fast, and it wasn't the best quality. And we're seeing that again with Web 2.0 stuff. So here are, basically there's two major categories that we're still seeing: cross-site scripting and SQL injection. We're still seeing them. So the first thing you should always do is hand review all entry points into your web thingamajig, and then all exits from your web thingamajig, whatever it is, whether it's client code, server code, gadget code, whatever. So you got like a request.read, then a response.write. That data, where did it go? Was it sanitized? Was it checked for validity? What? You should also seriously consider using the anti-XSS library from the ACE team. Works very, very well indeed. And also consider HTTP-only cookies. That means that if someone tries to read the cookie, because one of the attacks that people like to do is to read the cookie and then pass the cookie onto another domain. Well, if you have the cookie marked, so set cookie, blah, 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 semicolon, HTTP only, then the browser, if you try to call document.cookie, you'll get an empty string back. You will not get the actual cookie back. SQL injection, this is all simple stuff. I mean, I hate to say it, but it's simple stuff. No SQL statements should be built using string concatenation. That is the law in the SDL. You can't do that. You should be using prepared statements at a minimum, using prepared statements. The other one to do is to deny access to the underlying tables and the underlying objects, and only grant access through stored procedures and views. That way, if you can break out of a stored procedure and go drop table foo, it doesn't work because you don't have access to the foo table. You only have access to it through the stored procedure, which severely restricts your degree of freedom in trying to exploit the system. I love LINQ. By the way, any of you use LINQ? I absolutely love it. I hate building SQL statements. I've never liked building SQL statements. I loathe it. The cool thing is the guys very early on recognized the SQL injection problem and have tried taking great steps to try to mitigate them using LINQ. So if you have this little statement up here in LINQ, well, let's just say the bad guy controls this thing down here, then this becomes a parameterized query. That's a parameterized statement in here automatically, which will immediately nullify the potential attack vector. I'm not saying don't just blindly pass in untrusted data into here, but if you did, there are at least defenses in place, which may eventually get circumvented, but at least in the very early days, it looks like it's a pretty good defense. And the guys are hardcore about this. So if you guys know about SQL injection attacks and you're using LINQ, try to break it. And if you do break it, let us know before the end of the month, as I discovered this morning. So can you do it tonight, just in case? All right, next one. This is my little area of concern. Is anyone here built gadgets, widgets, Windows Live gadgets? So what's interesting about gadgets is they're basically HTML, JavaScript, SMS controls. I mean, any kind of mobile code, really. Even Silverlight, you can build them in Silverlight. In fact, if I had my way, this would have been a total Silverlight environment. But we shipped Silverlight a little bit too late relative to Windows Vista. The problem here is that if your gadget renders some untrusted data, you've got a cross-site scripting bug, which means that you can call things like, where is it? Oh, yeah. System.sidebar.execute, which basically means you can run any code that you want at that point. So it's a difficult problem to solve in many cases, because here's an example. I've got a couple of gadgets here. This is Redmond Junior High School or Austin Bergstrom International Airport. Well, where does that data come from? It comes from a web server somewhere. Is it untrusted? Absolutely it is. Why? I have no idea what computer I'm communicating with. No clue. Why? Because that communication using XML HTTP out to the back end is not over SSL. So you don't get the strong authentication that you would get from SSL. So you don't know where, so you've got to validate that data is correctly formed and then echo it into your gadget. Remember, this little puppy here is a mini HTML canvas. That's exactly what it is. So you're opening yourself up to cross-site scripting bugs, which basically means you can run any exploit code you want. So the first thing you should do is review, look at all incoming data. In the case of gadgets, most of that will come from XML HTTP calls. Make sure, have a check straight after to validate the data is well formed and correct. Then code review all calls to inner HTML document. Eval is one letter away from evil, and there's a good reason for that. If you're using eval, you may as well just go and send an email up to bug track just now and just say, hey, we're using eval. Email us when you find the bug. Because the eval is just bad. It's just bad. It's basically take some arbitrary string and run it, which is kind of bad. Inner HTML, we found people call inner HTML when they really should have just been calling inner text. So someone gives you some script tags, they will just get rendered as text. 90% of calls that we've seen to inner HTML would have worked perfectly well calling inner text, which is safe. David Ross and myself wrote a document called Inspect Your Gadget, which is available up on M. Yeah, it was his idea, not mine. He named it that, not me. It's up on MSDN. If you are building gadgets, please read the document. There's things in there I can almost guarantee you don't know. And Dave's like the #1 guy when it comes to cross-site scripting bugs in the world. So he actually invented them. So he knows a few things about them. So yeah, go ahead and read the document. Okay, quick call to action, and then we're done. It's exactly 7 o'clock. Evaluate the SDL. I mean, look at what we've done in the SDL and see how you can apply some of those ideas to what you do. It does work. Do not think for 1 minute that just raising the quality of your software will improve the security of the software. It is not true. But if you find some data that proves that it is true, please tell me. But I've yet to see anyone give me appropriate data. Use all the available tools. This is one of the reasons why we are so hardcore at Microsoft about always using the latest versions of the compiler. Windows Vista was compiled with the Orcus compiler, the Visual Studio 2008 compiler. We shipped that at the end of this month. We shipped Windows Vista a year ago. I mean, that's how good the quality of the code is in the compiler. I mean, you don't often ship an operating system with a not released compiler. But we do because the defenses were so good and continue to be good. Engineering, remove banned APIs. At least don't write new code with banned APIs. Just don't. And same with weak crypto. Don't write new code that uses MD4, MD5, SHA-1, DES, triple DES, RC4, so on and so forth, unless you have a very, very good reason to do so. If you're writing C and C++, compile with GS. It's free. In fact, if you're using Visual Studio 2005, if you don't say anything, you get GS for free. And find a link with the other 3 options, NX Compat, Safe SEH, and Dynamic Base, because it'll get you a whole bunch of defenses for free for doing nothing. I literally added this slide like the very last minute. We're actually going to be giving some copies of the SDL book away at the booth 22, straight after this session. So make your way down if you want a free copy of the book, and I'll even sign it for you, which adds exactly 35 cents to the value of the book on eBay. But I'll sign it for you. And with that, it's 7, and I am done. Thank you very much for your time.